going to be looking in 1.5 about infinite limits. We're going to need to be able to demonstrate what it means for a value of a function to approach infinity. Identify vertical asymptotes. That should be somewhat of a review for us from pre-calc, and then determine infinite limits. So we want to go ahead and look at this as a graphical approach first, and then we'll do it more analytically. So we want to be able to look at a graph and determine, especially from one-sided limits, whether or not our limit is going to be unbounded to be either infinity or negative infinity. And so we're going to be able to identify for one side and then two sides as well. So let's look at some examples here. And so what I have is I have a function and its graph. And so if you take a look right here, we have the function f of x is equal to 3 over x minus 2. And I went ahead and graphed that right above it. And so it's this rational function with a vertical asymptote of 2. And so the question is, what is the limit as we approach 2 from the left-hand side? And so what we want to do is from the left hand of 2, which is our vertical asymptote, so we're going to be really on this part of the function. And if you take a look here, what's going on is that we're sort of diving down. Now, we'll never get to 2 because that's a vertical asymptote. It's undefined value. But what we're doing is we're getting arbitrarily closer and closer to 2. And so for our x value, we want to know what we're getting close to for our y value. Well, if it's dropping forever and ever, that means what we're heading towards is negative infinity. And so what we would put is negative infinity as our limit. Now, we'll notice this at the bottom here, but I'm going to go ahead and say it, is the equal sign. Understand it doesn't mean equals, because infinity and negative infinity are not values, so it's not going to equal a negative infinity. But because technically the limit doesn't exist, and we had mentioned that a little bit in one of our sessions. So when the limit says it equals negative infinity, technically that limit does not exist. And so even though it's a D and E, we can say that the limit approaches negative infinity. It allows us to do some work with that. If we look at a limit as we approach 2 from the right, what we have is we're going to be taking off. And so instead of approaching negative infinity, we'd be approaching positive infinity. And so if I did say something about like a two-sided limit, you can see that these two things do not match up. And so the two-sided limit would be for sure a D and E because the limit from the left does not equal the limit from the right. Looking at an example over here where it's more like 1 over, something like 1 over x minus 3 squared. So it's an Atari type of function. What we have is the limit from the left. It looks like we've taken off, and so the limit from the left is infinity. And then the limit from the right is also infinity. And so what we have in this case is that if I said, what is the limit as x approaches 3, let's do the two-sided, of that function right there, we could just say infinity because the limit from the left and the limit from the right are the same. They're infinity. But what does that mean is that it still means that the limit doesn't exist. It just means that from both sides, it's infinity because it's unbounded or without bound. And so you can see that definition at the bottom is an infinite limit is where a function increases or decreases without bound. It goes on and on forever is what that means as x approaches some c value like 2 and 3 in the two examples that we did. But again, keep in mind the equal sign does not mean that the limit exists. The limit actually fails to exist in both of these instances. Okay, moving along a little bit, again, keep in mind we're going to be looking at these graphs. And what we're going to do is just look at what is the limit of f of x, and we're going to do it for both graphs here. So let's look at graph 1, and we're going to find the limit as we approach from the right and from the left. And so what is the limit as we approach 1? Here's 1. So as we arbitrarily get close to 1, what is my y value? Well, my y value is heading really off the screen, and so that would end up being infinity. Now, if I said, what is the limit as we approach 1 from the left? In this case, we're heading off the screen, but in the other direction, that would be our negative infinity. And so these infinite limits. Looking at the second example, again, looking at it from the right-hand side first, what we have is from the right of 1, we take off, and so it's going to be infinity. It does not meet anywhere. You don't even have to, since there's a vertical asymptote, you know that these aren't going to meet. So it's not like something that up here there's going to be like a corner where they meet, and we just don't know. No, we know that these things are going to be bounded to the right of 1 and to the left of 1, so they go up unbounded or go down to where they're unbounded. So the limit as x approaches 1 from the left side, you can see it also takes off, and so that's also infinity. And so that's the graphical approach. Now, we want to extend that out and look at how to do it analytically, and we'll see that in just a moment. Before we do that, though, we want to go ahead and investigate a little bit of a vertical asymptote. So taking us back a little bit to a pre-calc here. So the process of locating a vertical asymptote is, first off, we got to remove what we call the removable discontinuities, because the vertical asymptotes are non-removable. Those are our VAs. So in order to find these vertical asymptotes, what we want to do is we want to remove any holes or point discontinuities so that we can have just the non-removable left. So let's identify all the discontinuities first. So when we look at the first function, we set each factor in the denominator equal to 0. Well, 2 will not equal 0. That's an untrue statement, but x plus 1 could equal 0 at negative 1. And so what we have is we have an undefined value at negative 1. Now, I'm unable to remove that discontinuity, the factor that produces that discontinuity from the problem. There's nothing to cancel up top. So this is what we call a non-removable discontinuity. Therefore, that's a vertical asymptote. Looking at the second example, again, we have a fraction, so we factor fractions first. Now, what you'll notice is the numerator is the sum of two squares, and that really goes to complex. We don't do complex in Calc 1, and so there's no way to factor the sum of two squares, but there is the difference of two squares at the bottom, and that's going to allow us to find our two undefined values. So the numerator is prime. The denominator, what we find is we find that negative 1 and 1 are our two undefined values, but can either one be removed from the problem? Neither one can be canceled with the numerator, so they both are what we call non-removable discontinuities, and that means both of these are vertical asymptotes. So we'd have a VA at 1 and negative 1. Looking at the last one, we look to factor, and it looks like the numerator should be able to be factored. So let's see if we can do that. And so we get x plus 4 and then x minus 2. And then in the denominator, it's the difference of two squares, so x plus 2 and x minus 2. Okay, so the two undefined values, the two discontinuities, are negative 2 from that factor and 2 from that one. So we've got negative 2 and we've got a positive 2. Those are our discontinuities. Now, which one are the non-removable? Well, if you notice, one of them, the 2, can be removed. So the 2 is not a VA. It is a discontinuity, but it's not a non-removable, it's a removable discontinuity. So the only vertical asymptote that we've got is x equals negative 2. So we have a VA there and have a hole or something around the value of 2. Okay, so let's go ahead and let's look at determining infinite limits, and we're going to be doing it a little bit more analytically. So there's some properties here we want to just get in our notes and be comfortable with. Again, fairly intuitive a little bit. What we have is that if we find the limit of f of x as x approaches c, and let's say we get infinity, okay, positive infinity. And then we have another function g, and the limit of that is just L, some number, okay, some number L type of thing. This should be a c, not an x right there. Okay, and so when we use the sum or difference of these two limits, just think about it sort of intuitively a little bit, just like if you're a little kid. If I said something like, because if we go back to our limit that we did like in 1.3 where we had all of our properties, what we could do is we could rewrite this right here as the limit of f plus or minus the limit of g. Now the limit of f is infinity. So really what we're getting is infinity plus or minus a constant. So infinity plus or minus just some constant we call L. Well, infinity plus L, a constant, is simply going to be infinity, and L is not bigger than infinity, so infinity minus L is still going to be infinity. We're not even going to touch it. Now, if it's the other way around, if it's L plus or minus infinity, now things look a little different. I mean, think about it, again, just think of it sort of intuitively. If we have a constant plus infinity, that would be infinity. However, what's a constant minus infinity? Well, we're removing more than what we started with, and so that would have been negative infinity. So we definitely could get a negative infinity as one of our answers for those. Product is going to be very similar. Just think about your signs, but if you have infinity times a constant, infinity times a constant, simply infinity, as long as the constant is positive and as long as our infinity is positive. Which it is in this case. Okay, but go back to a negative times a negative is a positives and such. So if we look over here and let's say our limit is less than zero, it's a negative. So we're going to have a positive infinity times a negative constant of some sort. So whatever, let's say -4 or something like that. Well, first off, infinity times 4 is just infinity, but what's a positive times a negative is negative. So just utilize your signs, you should be fine. The quotient one we'll use a little bit as we get going, but later with some things, but it's an interesting one where we get 0. We'll see this a little bit in 3.5. And so this idea of if we have infinity on the bottom and then we have some constant on the top, well, what we have is arbitrarily, we just are so close to 0, we call it 0. So L over infinity is simply 0. So that's what the last one is. So we're going to go ahead and take a look at some other little things to throw in your notes. These are flashcards, that's why the stars are there. But what we have is we have this idea of a constant over 0. Okay, so when we go back to 1.3 and look at the bottom of the screen here, when we had 0 over 0, which is an indeterminate form, one of the types of indeterminate forms, but what that told us is we can go to work. We can do something. We can either factor, we can have a complex fraction, maybe it's rationalized in the numerator, maybe it's a trig, but something can be done to simplify this and allow us to do a direct substitution when it comes to limits. Now, eventually, what are we going to remember? We're going to get 0 over 0. We should go, oh, we're going to L'Hopital that thing. Okay, we're going to L'Hopital it real good. But right now, we don't know that. So again, 0 over 0 means we can do some things. You just have to do some other means to solve it. Now, what if we don't get 0 over 0? What if we get a constant over 0? Anytime you get a constant over 0, there's no more work to be done. You cannot simplify this any further. What it implies is that you're either going to have positive or negative infinity as your solution. So we already know when it's a constant over 0, it's either going to be infinity or negative infinity. We just got to decide which one is it. So what we do is we label the signs that are out in front of our constant and our 0 are going to come into play. So positive over positives, positives, and such. A positive over a negative is negative. Now, the constant's an easy one. When we get it, it's automatic. Like we get a 3, we know it's positive 3. Or if we get -2, we know, oh, that's -2. So the constant, I'm not too worried about it. It's the 0. We're either going to have positive zeros or negative zeros, and that depends on which way we're coming towards 0. Which way we're approaching the 0. So if we're approaching 0 from the right-hand side on a number line, that's what we call the positive side. So if we're approaching 0 from the positive side, it's going to be a positive 0. If we're approaching 0 from the left-hand side or the negative side, then that would be a negative 0. And then once you label those, then it's either infinity or negative infinity. We just got to figure out the signs. And so a positive over a positive is positive infinity. Or a negative over a negative is also positive infinity. Okay? So you already marked infinity to the right. We just got to figure out if it's positive or negative infinity. So we'll definitely take some time here when we do it analytically and figure out, well, how do I know if the 0 is negative or if the 0 is a positive one? Which way are we approaching it from? So that's what we're going to do here on the last slide. Look at these examples. So we have a limit here. We try a direct substitution. That's always the first thing we try. And when we do that, we end up getting 4, because the opposite of -4 is 4. And on the bottom, we get 0. So when it's 4 over 0, that means I can't really do anything with this. That means my answer is either infinity or negative infinity. I just got to figure out which one. Now, 4 we already know is positive, so no issues there. It's the 0 we've got to figure out. What's the sign that goes in front of our 0? So I come and look and see, okay, well, I plugged in -4, and notice that I'm coming from the right-hand side. So the little plus sign up here tells me I'm coming from the right-hand side. So if you think of a number line, and here's -4, if I'm coming from the right-hand side, and again, it's going to be like right next to -4, but anything from the right-hand side of -4 would be fine because that's the direction I'm coming from. All I'm doing is stealing the sign. It's the Houston Astros all over. I'm just stealing signs here. I've already established it's a 0. I've already established it's a 0. All I'm doing is figuring out is that 0 going to be positive or negative. So think of a number that is to the right of -4. That is larger than -4. Some students will just go to 0. They'll be like, 0 is bigger than -4. It doesn't matter. What you do is you simply plug in 0, and all you're doing is stealing the sign of what you get. So 0 plus 4 is a positive 4. We steal the sign, and now we know that's going to be a positive infinity. Looking at the second example, exactly the same function, but now we're coming from negative 4 from the left-hand side. So once again, we get positive 4 on top. That doesn't change. And we get a 0 on the bottom. We just got to figure out what our 0 is. So on a number line, you want to think of, here's negative 4. We want to think of a number that's to the left of negative 4. So most students will pick like negative 5 or something like that, something that's smaller or to the left of negative 4. So if I plug in negative 5, I get negative 1. So we don't want to put negative 1 down here. It's already 0. All I'm doing that for is to steal the sign. That's all I'm doing it for. And then we already know this is going to be either infinity or negative infinity. And so a positive over a negative is negative, and we know it's negative infinity is our infinite limit. Looking at number 3. Now this one you can sort of intuitively know what the answer is going to be, but let's go ahead and look at it anyways. And the reason I say that is because of the square. Okay, and so I'll show you that in just a moment. But we're going to take the 1 and plug it in. There's nothing on top, and so it's a positive 1 on top. On the bottom, we definitely get a 0. Okay, and the question is what kind of 0 we get? And what I meant by is fairly intuitive is no matter what side I come from, if I square a value, isn't it always going to be positive? So you can try from the right-hand side of 1. Just plug in 2. 2 minus 1 gives you a positive 1, and a positive squared is positive. And remember, all I'm doing is stealing the sign. Don't put the number there, just put the sign. We already know this is going to be infinity or negative infinity. We just got to figure out the sign of it. Looking at the same function but coming from the left of 1, again, we have positive 1 on top. We have 0 on the bottom. We know this is either going to be infinity or negative infinity. We just got to figure out what our sign is. If you pick a number to the left of 1, let's say 0. So again, just to make sure that makes sense to you, I want to pick a number that's smaller than 1. So how about 0? 0 minus 1 is negative, correct? But I'm squaring it. So it's negative 1 squared, which is a positive 1. So once I simplify the denominator, once I establish what the denominator is, then I can steal its sign and I get positive infinity. So, and the graph of this is an Atari, so that makes sort of sense as